In September of 1898, a mining engineer named Daniel Cowan Jackling stood in a canyon west of Salt Lake City with another engineer, Robert C. Gemmell, and held samples of ore that every experienced mining man in the West had rejected. The ore was porphyry copper, finely disseminated through granite and quartz. A single ton of ore contained roughly 20 pounds of copper. That was all. The mining industry's rule was absolute. Strip the high-grade material, leave the rest. Jackling and Gemmell wrote a report, dated September 18, 1898, proposing to do the opposite. They proposed to move the mountain. They proposed to build steam shovels, lay railroad track directly into the pit, construct a mill with a capacity of 300 tons per day, and process ore that every mining operator in America said was economically impossible. The report was submitted to Joseph R. de Lamar, the mining capitalist who held the property. De Lamar read it and walked away. The ore was too low grade, he said. It could not be made to pay. 5 years would pass before Jackling found investors willing to believe in an impossible idea. When they came, his gamble would either build American mining or destroy him. Before you can understand what Jackling was committing to, you need to understand what the mining industry saw when it looked at Bingham Canyon. The ore graded less than 2% copper. That meant mining 2 tons of waste rock for every ton of ore. Every engineering textbook said this was uneconomical. The profit margin was too thin. The processing cost was too high. The equipment did not exist. No mill had ever been designed to process 300 tons of ore per day. No railroad existed to haul that volume. No steam shovel had ever loaded ore on the scale he was imagining. He was proposing to build an entirely new industrial method on land that held ore worth mining only if the method worked. If it failed, the canyon held nothing. In 1903, 5 years after the Jackling-Gemmell Report was rejected, Daniel Jackling finally found his backing. Charles McNeil, Spencer Penrose, and Enos Wall agreed to organize the Utah Copper Company. They capitalized it at a level nobody had ever risked on a low-grade deposit. The Guggenheim family, one of the wealthiest mining interests in America, agreed to finance the venture. $3 million was committed to a 300-ton-per-day mill at Copperton. That was enormous capital for 1903. It was also a commitment with no certainty of return. Jackling was betting that he could build a system nobody had ever built before. His investors were betting that he was not insane. In 1906, Jackling brought steam shovels to Bingham Canyon. They were not theoretical machines. They were the same type used on the Panama Canal, massive, powerful, built to move earth on an industrial scale, but they had never been used to load copper ore in an American mine at volume. Each shovel weighed over 100 tons, mounted on a heavy steel frame riding on rails laid directly into the pit. The shovel stood on 2 rails, and the operator, standing in an open cab exposed to the sun and the pit dust, controlled a boom that extended nearly 40 feet out over the loading face. At the end of that boom hung a dipper, a bucket, that could hold 3 tons of ore. The cycle was simple in theory but demanded precision. Position the boom, lower the dipper to the face, crowd the dipper into the ore with hydraulic pressure, raise the loaded dipper, 3 tons of copper ore hanging from the boom. Swing the entire boom 70 degrees across the tracks. Deposit the dipper into a waiting railroad car. Retract the dipper. Repeat. The entire cycle had to take less than 60 seconds. Jackling's mill demanded 300 tons of ore per day. That meant each shovel had to load approximately 100 rail cars per shift, roughly 1 car every 6 minutes, 10 hours per shift. No stopping for adjustment or repair or rest. The operators who ran these shovels were learning a machine that had never been used this way before. They were teaching themselves through production pressure. By late 1906, Utah Copper Company had deployed 8 steam shovels across the pit. The first shipment of ore left Bingham Canyon in December 1906. In June of 1907, the first copper concentrate arrived at the Garfield smelter. The ore grade was exactly what Jackling had predicted, between 0.7 and 1% copper. The flotation concentration process he had developed with Robert Gemmell took the scattered ore and recovered it at 25 pounds of copper per ton of ore processed. Raw ore went into the Copperton mill. The ore was crushed to the consistency of powder. Then it was mixed with water and chemical reagents, oils that caused copper mineral particles to float while waste rock sank. The copper particles rose with the froth, were skimmed off, and were concentrated to a slurry containing 28% copper. That concentrate was piped to the Garfield smelter, dried, and placed in a flash furnace where the copper was reduced to pure metal. For the first time, Jackling's system had not failed. It had worked. But here was what the mining industry did not yet understand. The system was not complete. 8 shovels were not enough. The railroads were working, yes, but only because production had not yet reached the scale Jackling was designing toward. By 1909, the number of shovels had grown to 9. By 1912, the demand for additional capacity had forced Boston Consolidated Mining Company and Utah Copper Company to merge, a consolidation that unified all open-pit operations in Bingham Canyon and created a single integrated mining and milling operation. Jackling had understood from the beginning that low-grade mining was not a single machine problem. It was a system problem. One shovel loading ore at the wrong rate would stall the mill. A mill processing ore too slowly would back up the railroad. A railroad that could not haul the concentrate would stop the smelter. Every component had to work in precise sequence, or nothing worked at all. By 1912, Bingham Canyon was the largest industrial mining complex in the world. That statement requires precise understanding of what largest meant. It did not mean highest production per man. It did not mean deepest pit or richest ore. It meant that Jackling had built an integrated system capable of removing 200,000 short tons of copper ore per year. But that also meant removing 400,000 tons of waste rock every year. Think about the scale. 2 tons of rock had to be moved, broken, hauled, and dumped for every single ton of ore. The railroad had to run continuously. The mill had to process 300 tons of ore per day without stopping. The flotation tanks had to work 24 hours a day. The Garfield smelter had to turn that concentrate into pure copper without interruption. Every system had to feed the next system. If any link broke, the entire chain stopped. By 1912, Utah Copper Company had become the largest non-ferrous metal producer in the United States. The annual output was approaching 200,000 tons of ore. World War I had not yet begun, but copper demand was rising. The smelters were running full capacity. The railroad was moving trains. The shovels were loading continuously. And Jackling was already planning the next phase, expanding the mill, bringing in more shovels, deepening the pit. The mountain was not a mountain anymore. It was becoming a pit. Between 1912 and 1917, Bingham Canyon became the center of American copper production. By 1917, the pit was producing at rates that seemed impossible. The Deseret News reported in December 1917 that the mine had reached its greatest tonnage in history. During that year alone, according to the same report, the copper and other metals from Bingham were being sent to France, Italy, Russia, and across the entire globe. The United States was fighting in World War I. Copper demand was unlimited. The military needed copper for ammunition, for electrical systems, for every piece of military technology. Jackling's low-grade pit could now produce copper faster than any deep mine in history. But this created a different problem. The equipment was wearing. The 9 steam shovels that had served from 1906 through 1912 were running continuous shifts. A steam shovel designed to run 8 hours a day in normal mining was now running 16 hours a day, 5 days a week, moving ore that had to be processed and smelted immediately. The boilers were burning coal constantly. The dipper handles were cracking from the repeated stress of loading heavy ore. The railroad tracks were wearing from the constant passage of loaded cars. Jackling had designed a system that worked, but working the system flat out, at wartime production rates, revealed an uncomfortable truth. The equipment would not last as long as the ore would last. The pit would outlive every machine in it. This meant that Jackling had to plan not just for production, but for replacement, for an endless series of new shovels, new locomotives, new mills. The cost of renewal was becoming as significant as the cost of operation itself. Jackling understood something about machine mining that the industry did not. The operator was not separate from the machine. The shovel operator and the shovel were one system. A man who learned to load 3 tons of ore in 60 seconds, who knew exactly how much pressure his dipper could take before the teeth tore into solid rock instead of broken ore, who understood the rhythm of pit work. That man was not replaceable. He carried knowledge that no training manual could transfer. An operator who had worked the same shovel for 3 years knew its quirks, its weak points, the way the boom wobbled slightly on the downswing, the precise moment when the crowd pressure reached maximum load. He knew when to hold the load for an extra half second to let the rock settle into the bottom of the dipper before raising it. He knew when the pit face was about to collapse because he could read the angle of the cliff in the afternoon light. This knowledge lived in his hands and his judgment, not in the machine. Jackling paid his shovel operators well, better than construction workers in the canyon, better than any labor the region offered. He understood that the machine would fail, but the man who operated it might learn something that could be applied to the next machine. By the end of 1917, hundreds of men had worked in the Bingham pit. Some had quit, some had been injured, some had stayed for years. The institutional knowledge in that group of men had become the actual operating manual of the mine. Jackling had accidentally created a system where the value of the pit depended not just on the ore body, but on the core of experienced operators, mechanics, and engineers who had learned to manage the system under production pressure. The pit was producing because the men who worked it understood how to handle both the rock and the machines that moved it. Daniel Cowan Jackling retired from Kennecott Copper in 1942. He died on March 13, 1956, at age 86 in San Francisco. By the time of his death, Bingham Canyon had produced approximately 16 million tons of copper, more than any mine in American history. The pit had grown to 2.5 miles wide and 3/4 of a mile deep. During World War II, when the nation's entire industrial capacity was focused on defeating Japan and Germany, Bingham Canyon supplied 1/3 of the copper used by Allied forces. Not 1/3 of Utah's copper, 1/3 of America's copper, 1/3 of the entire Allied copper supply. The operation that Jackling had bet his reputation on in 1903, the idea that low-grade ore could be profitably mined at industrial scale through mechanization and integration, had become the largest copper producer in the world. The system he had built outlived him by decades. By the 1980s, when modern automation began to replace human operators, Bingham Canyon was still running the system Jackling had designed, still using open-pit mining, still using the railroad to haul ore, still using flotation concentration to separate copper from waste. The machines had been replaced. The operators had been replaced by automated systems. But the core system remained unchanged because Jackling had understood something fundamental about low-grade mining. Scale defeats grade. If you can move enough material, cheap material is as valuable as expensive material. If you can process enough ore, each ton can yield profit. If you can integrate all the steps, mining, hauling, milling, concentrating, smelting, into one system where one failure stops everything, then you can optimize each step. Jackling had built that system. He had bet everything on it, and it had proven him right. The pit is still open, still producing. The ore still runs less than 1% copper, and Jackling's 1903 decision to move the mountain anyway, to commit an impossible bet, proved to be not impossible at all. It was inevitable. It was the future of American mining. The ore does not acknowledge the machines that moved it. It was always just rock. The skill was in knowing what to do with it.